All right, let's dive into some theoretical physics. We've got this research paper, and the title sounds pretty intense, on an axiomatization of path integral quantization and its equivalence to Berezin's quantization.
Yeah, it's a bit of a mouthful. But honestly, the ideas in this paper, they're pretty mind-blowing, even for someone like me who works with this stuff every day.
So for this deep dive, can we get a roadmap? Just to make sure we don't get lost in the weeds.
Definitely. So this paper really boils down to wanting to make the math behind path integrals even stronger, more rigorous.
Okay, and path integrals, those are all about how, in quantum mechanics, a particle takes every path at the same time, right? Not just the most efficient path, but like all possible routes.
Exactly. It's like, imagine an electron. In the everyday world, we'd try to map out its path, kind of like predicting where a thrown ball will land. But quantum mechanics throws that idea out the window. It says, nope, that electron, it's taking every path at the same time, like a wave rippling outward. And path integrals are how we actually do the math on that.
So that's our foundation, path integrals. What's the next step this paper takes?
Well, it gets into quantization. Basically, that's the process of going from our normal classical physics, the world we see every day, into the totally different rules of the quantum world.
So to really get the universe at its most basic level, we need to figure out how to go from regular physics to the quantum kind.
Yeah, you got it. And this paper is all about improving the tools we use to do that, particularly for spaces with a specific geometric structure. These structures are super important to physics, and you can kind of think of them like the scaffolding for understanding how particles act in the quantum world.
Is that where this axiomatization comes in from the paper's title?
Exactly. It's like figuring out the ground rules for how path integrals work, the fundamental axioms. In math, axioms are like the bedrock. They're the starting truths that you use to build everything else upon.
So making sure our calculations, our predictions about quantum stuff are as accurate as possible, but there's more, right? Didn't this paper also bring up Berezin's quantization?
You're on top of it. There's definitely more to it. See, Berezin's quantization, that's another way to think about this whole quantization thing. But instead of path integrals, it uses these things called operators.
Operators. Okay, like what exactly is an operator in this context?
So you could think of an operator kind of like a function that works on other functions, changing them in very specific ways.
So we've got two ways of looking at this quantum world. Am I sensing a but here's the twist coming up?
You're catching on quickly. The amazing part is that this paper shows these two methods, path integrals and Berezin's quantization, they're deeply connected. They actually show that under certain conditions, they're mathematically the same.
Whoa, so it's like finding out two completely different maps of a city lead to the exact same place. Finding unity where you didn't think it existed.
It's a great analogy. This kind of discovery, finding unity like that, it suggests we're really onto something fundamental.
I'm starting to see why you called this mind-blowing earlier. We're basically taking these super complex mathematical tools and using them to try and piece together the universe's building blocks. All right, lay it on me. What else does this paper get into?
So from here, the paper dives into coherent states and how they connect to the Heisenberg uncertainty principle.
The uncertainty principle, that's the one where you can't know both the position and the momentum perfectly at the same time, right?
Exactly. It's a fundamental limit in quantum mechanics. And coherent states, they're interesting because they represent the states that come closest to that classical physics behavior, that well-defined behavior we see in everyday life.
So it's like, even though we know the quantum world is fuzzy, are coherent states kind of like trying to draw a nice, neat dot on a graph to represent our particle?
I like that analogy. They're the quantum states that kind of resemble those predictable objects we see in the classical world.
I think I'm following it too. But how does this tie back into path integrals and Berezin's quantization? I feel like we're juggling a lot here.
We are.
Yeah.
It's a lot of interconnected ideas.
Yeah.
But that's what's so cool about this paper. It ties them all together really elegantly. Remember we were talking about quantization, that process of going from classical physics to quantum. This is where coherent states come in. They help build a bridge.
So instead of particle being a point, now we're talking about it as this fuzzy coherent state. And then we'd use path integrals and Berezin's quantization to see how these states change over time.
You got it. It's like we're upgrading to a super high-resolution camera lens. We get a much clearer picture of how these systems behave.
This is wild, but I gotta be honest, it's getting pretty abstract. Does the paper give any, like, concrete examples to show how these ideas actually work?
They do. They use the example of a sphere. Now, that might seem simple, but it actually has a lot of the same mathematical properties as way more complex spaces that physicists deal with.
A sphere. Like a basketball. What's that got to do with quantum mechanics?
Okay, so picture that basketball. But instead of being solid, it's like a surface representing all the possible states our quantum system can have. The paper shows how you can use path integrals to calculate the probability of our particle moving from one point on the sphere to another.
Okay. I think I see where you're going with this, but why a sphere? Is it just because it's a simple shape?
It's a bit more than just simplicity. See, a sphere is what mathematicians call a symplectic manifold, those geometric spaces we were talking about before. Turns out, a lot of systems physicists study, things like particle motion in a magnetic field, they can be described mathematically using these symplectic manifolds.
So it's like we're using this sphere as a testing ground for these really complex mathematical ideas.
Exactly. Like a physicist's playground. They can experiment with theories and see if they hold up. And the amazing thing is, by using this example of a sphere, they find this really interesting link to something called polymatrices.
Polymatrices. Oh man, that rings a bell like way back from quantum mechanics class. Vaguely.
Don't worry, it all comes back eventually.
Yeah.
Polymatrices are these mathematical objects, and they're super important for describing the spin of a particle.
Right, spin. That's like how an electron can be spinning up or down, right?
Exactly. And get this whole concept of spin, it's deeply connected to the geometry of the sphere. It's like there's this hidden link between how an electron spins and the shape of a basketball.
Okay, that's officially blown my mind. So we've got path integrals, Berezin's quantization, coherent states, the uncertainty principle, and they're all like connected to spinning particles on a sphere. This is wild.
It's all connected in this beautiful, crazy way. And the paper keeps going. It actually takes things even further into some even more abstract math.
Wait, there's more. Don't leave me hanging. What other mathematical rabbit holes does this paper go down? You were saying this paper goes beyond the sphere into even more abstract math.
It does. We go from spheres to something called Poisson manifolds.
Poisson manifolds. Sounds even more intense than symplectic manifolds.
Are we about to hit a math singularity here? No singularity here, don't worry. We're still grounded, even if it takes some pretty high-level math to get there. Basically, Poisson manifolds. Think of them as a broader category of those geometric spaces. They're a bit more flexible, less rigid in their structure than symplectic manifolds. And that flexibility, it actually makes them better for describing certain physical systems.
Okay, so it's like we're upgrading our math toolkit, going from hand tools to like industrial grade stuff.
Exactly. And this paper shows how those tools can handle quantization for spaces that used to be, well, really tough, even considered impossible with the usual methods.
Now I gotta know, what kind of spaces are we talking about? Give me an example.
All right, so they get into things like the Poodle sphere, which is kind of hard to picture, but essentially it's a sphere with some very specific geometry. And they even get into Riemann surfaces.
Riemann surfaces. Now those, I've heard of at least, aren't those the shapes mathematicians use to study complex functions? Like the ones that look like donuts and pretzels and all that.
That's them. And what's amazing is this paper shows how you can use those path integral techniques even on these complex spaces, which could totally open up new research in things like quantum gravity, even condensed matter physics.
This is all incredible, but I gotta ask, why should I, someone who's not a theoretical physicist, care about this stuff? I mean, it's fascinating, but it seems pretty far removed from everyday life.
That's a fair point. But here's the thing. These abstract mathematical ideas, they often have real-world results. This whole quest to understand quantization, to bridge that gap between classical and quantum physics, it's already driven crazy advancements. Things like quantum computing, new materials, even how we understand the universe's very first moments.
So next time I'm using my phone or looking at a picture from space, I should be thanking a theoretical physicist for pushing the limits of math.
Exactly. It reminds us that even the most abstract research can have a huge impact on our lives.
You know, as we've been on this deep dive, it's really struck me how much this paper emphasizes making connections between different parts of physics, different math concepts.
Yeah, it's crucial, like putting together a massive puzzle. Each connection, whether it's path integrals and Berezin's quantization, or a particle's spin and the shape of a sphere, it gets us closer to the big picture.
And in this case, the big picture is what? Figuring out how to quantize these super complex spaces, which could then lead to breakthroughs in all sorts of areas.
You got it. It's all about pushing the boundaries of what we know, using math to explore the universe's biggest mysteries.
Well, I think that's about as deep as we can dive today. A huge thanks to you for being our guide through this wild world of theoretical physics.
Happy to do it.
And to everyone listening, thanks for joining us. Remember, the universe is full of mysteries, so stay curious and keep exploring. We'll see you next time. Ever wonder how physicists go from describing the universe with like smooth, curvy spaces to the neat but sometimes bizarre world of quantum mechanics?
It's like trying to fit a rainbow into a paint-by-numbers set.
Yeah, exactly. And that's what we're diving into today, this crazy process of quantization.
And we're not just talking basic ideas here. We're going deep into cutting-edge research that could change how we quantize pretty much anything.
Oh, wow, that's a big claim. Our guide for this deep dive is this physics paper, and it's got a mouthful of a title, On an Axiomatization of Path Integral Quantization and its Equivalence to Berezin's Quantization.
Yeah, it's a bit of a tongue twister.
Don't worry, we're here to break it down.
Absolutely. Our mission today is to unpack all these complex concepts, especially this really cool new way of looking at path integral quantization.
Okay, path integral quantization. Gotta love those physics terms.
It's basically like, imagine trying to map out every single route a quantum particle could take.
Instead of just the one it actually does.
Yep.
Okay, I'm kind of intrigued, but let's back up a sec. For those of us who haven't completely lost ourselves in the quantum physics rabbit hole, what is quantization?
Okay, so imagine you're listening to this beautiful violin solo, all smooth and flowing. Now imagine trying to play that same melody but on a piano.
You'd have to, like, use the keys, right?
Exactly. You can't quite capture that same seamless flow, can you? You're stuck with those specific keys on the piano. That's kind of like the difference between classical and quantum physics. Quantization is the process of going from that smooth violin melody, the classical world, to the distinct notes of the piano, the quantum world.
Yeah. So we're taking the universe's symphony and figuring out how to play it on a quantum piano.
That's a great way to put it.
I like that analogy. But before we get too musical, you mentioned something earlier about path integral quantization, right? What's the path integral part of all this?
Right. So in classical physics, when you have a particle moving around, you can usually just draw its path, like a single line from point A to point B.
Right, basic movement.
But in the quantum world, things get a lot weirder. Quantum particles, they don't follow just one path. Instead, they're like exploring all possible paths at the same time, almost like they can't make up their minds.
Wait, all paths at the same time? Isn't that just like chaos?
It does seem chaotic, right? But it's also what makes quantum mechanics so darn interesting. Now, a path integral is basically a mathematical tool that lets physicists sum up the contributions of all these possible paths a particle could take.
Okay, I think I see why physicists might need a whole new approach to even begin to tackle this.
They definitely do. And that's where this research we're talking about comes in. Instead of trying to calculate this crazy complex path integral directly, which, let's face it, is often impossible, these researchers have found a really clever workaround.
Oh.
They've basically laid down a set of rules or axioms that any path integral must follow to make sense.
So it's kind of like they're setting the rules of the game without telling you every single move you have to make.
Exactly. And here's the really amazing thing. By doing this, they've found a direct link between their new way of looking at path integrals and this other crucial concept in quantum physics called Berezin's quantization.
Berezin's quantization, another one for the quantum physics glossary. What is that, and why is this connection such a big deal?
Okay, so picture this. You have this dictionary that not only defines words, but also tells you how to use those words in different sentences, like their grammar.
Right, so not just the meaning, but how the words actually work.
That's Berezin's quantization, kind of. It's like a special quantum dictionary that takes objects from the classical world, things like position, momentum, and translates them into their quantum versions, which are often these strange mathematical operators.
So it's not just a translation, it's like a set of instructions for how to use those translations in the quantum world.
You got it. And what's really cool is this paper shows us that the properties of those paths we talked about, all those possibilities the particle could take, they're actually what help define this quantum dictionary. They give us a way to figure out how these quantized objects actually behave.
Whoa, so we're using the very essence of quantum weirdness to make sense of the quantum world. That's pretty mind-blowing. And we haven't even gotten to the part about quantizing shapes. I think we need to give our listeners a moment to process all this. Stay tuned, because in the next part, we'll dive into the even weirder world of quantizing shapes.
It's really like we're trying to teach our good old classical physics dictionary to speak this whole new language of quantum mechanics.
Using the grammar rules of quantum particles. So last time we left off with this idea of quantizing shapes, and I gotta say, it sounds kind of like, I don't know, an art exhibit or something.
Yeah, it's a pretty wild concept.
What does it even mean to quantize a shape? And what kind of shapes are we even talking about here?
Okay, so picture a sphere. like a perfectly round globe.
Got it.
In classical physics, describing its properties, its curvature, surface area, all that, it's pretty straightforward. But in the quantum world, things get a bit messy. We can't just assume that a sphere at the quantum level will act the same way.
So we're trying to take this smooth, continuous sphere and make it fit into the blocky, discrete world of quantum mechanics.
Exactly. That's the challenge of quantizing a shape. Finding a way to describe its properties, using the language of quantum mechanics, those quantum operators we talked about before. And the reason physicists are so interested in this whole quantizing shapes thing is that these shapes can actually represent the very fabric of the universe.
Okay, now you're really blowing my mind. How can a simple shape represent something as mind-bogglingly complex as the universe?
Well, you see, Einstein's theory of general relativity tells us that gravity isn't really a force in the traditional sense. It's more about the curvature of space-time.
So instead of gravity pulling things together, it's more like space-time itself is being warped and curved by all the stuff in it, right?
You got it. And those curves, we can represent them mathematically using shapes.
Whoa, so if we can figure out how to quantize these shapes, are you saying we might actually be closer to understanding how gravity works at the quantum level? Isn't that like the holy grail of physics?
It's definitely the dream. And this paper takes a big step in that direction. It shows how this new framework, one connecting path integrals and Berezin's quantization, can be used to quantize not just spheres, but also even weirder shapes, surfaces with constant curvature. They even figured out how to quantize shapes with holes in them.
Hold on, holes.
Well,
Like a donut. Are you telling me we can quantize a donut now?
well, in a simplified mathematical sense, yeah.
That's amazing.
And it's a pretty big deal because it tells us that this method is way more versatile than we initially thought. If we can quantize shapes with holes, who knows what other possibilities open up. It could be the key to quantizing a whole bunch of other objects and spaces, even some that might get us closer to understanding quantum gravity.
Now, you mentioned that this research uses Berezin's quantization. Can we dig into that a little more? How does this whole quantum dictionary thing actually work when we're talking about quantizing a shape?
Right, so remember, Berezin's quantization gives us a way to translate classical objects into their quantum counterparts, right? So in the case of shapes, we're essentially translating these classical descriptions of curvature, area, all those geometric properties into the language of quantum operators.
Right, okay.
And the fascinating part is that the paper shows how the properties of those quantum paths we talked about, all those possibilities a particle could take, they actually help us define those quantum operators. They tell us how those operators act on our newly quantized shape.
So it's like those quantum paths are whispering the secrets of quantum geometry, and Berezin's quantization is the code book that lets us finally understand them.
That's a fantastic way to put it. This paper reveals this deep connection between those whispers, those paths, and the rules that govern them. We've been trying to make sense of them for years, and now it's like we're starting to understand the language itself.
That's incredible. We're venturing into some seriously uncharted territory here. But before we get totally lost in the quantum foam, I think we need to give our listeners a moment to absorb all this amazing information. So we've been talking about this new way of quantizing shapes, even ones with holes, which is wow.
Right.
But there's this one shape that's even crazier to think about in this whole context, and that's, well, the universe itself.
The universe.
Yeah. So where does all this research leave us in terms of understanding the biggest, most fundamental shape of all?
That's the big question, isn't it? I mean, this paper doesn't exactly give us all the answers, but it does give us some interesting clues. Because, the universe, according to Einstein's theory of general relativity at least, it's not this static fixed box we used to imagine. It's dynamic, it's curved, and it's constantly being reshaped by, well, everything in it.
So it's like instead of trying to quantize a simple sphere or a donut, we're actually dealing with this unimaginably complex, ever-changing shape of the entire cosmos.
Exactly. And that's where things get really, really tricky. But here's the cool part. This new framework, the one that connects path integrals and Berezin's quantization, it just might give us the tools to finally tackle this. Remember those Lie algebroids we talked about earlier?
Vaguely. They kind of sounded like something out of Star Trek, to be honest.
They do have a certain ring to them, don't they? But Lie algebroids are basically these powerful mathematical tools that help us understand what's going on behind the scenes in complex systems, especially ones that have a lot of symmetry.
Symmetry like what? The two sides of a face or a pattern on wallpaper?
Well, in physics, we're usually talking about more abstract symmetries, like the idea that the laws of physics should be consistent no matter where you are in the universe.
Okay, so how do these Lie algebroids help us with this massive universe-sized quantization problem?
Think of them like a blueprint or a map. Lie algebroids help reveal the hidden symmetries within these incredibly complex mathematical spaces, those quantum landscapes we mentioned earlier. And by understanding these symmetries, we can start to figure out how to quantize even the most challenging systems.
Including, maybe, the entire universe.
Potentially. It's like we've been lost in the woods, and this research just handed us a map and compass. We still have a long way to go, but at least now we have a sense of direction.
That's a great analogy. It's enough to make you want to go back to school for like a decade and get a PhD in physics.
I know, right?
Or at least to keep listening to more deep dives like this one. Well, that about wraps up our exploration into the mind-blowing world of quantization. Hopefully you're walking away feeling a little bit smarter, a little bit more curious, and maybe even a little bit more in awe of the universe and all its mysteries.
And as always, if you want to dive even deeper into all this, we've got links to the original research and some more accessible explanations in the show notes.
So check those out. Until next time, keep those minds open and keep on exploring. You know, it's like we humans, we think we've got it all figured out. Like we've cracked the code with gravity, electricity, you name it.
Yeah.
And then bam, quantum mechanics comes along.
Right.
And suddenly all our neat little rules go out the window.
It's true. The universe at that subatomic level, it plays by a whole different set of rules.
Totally. It's like we've stumbled into a whole new reality show.
Absolutely. It's wild.
Yeah.
And that's exactly where we're headed in today's deep dive.
We are. We're tackling a paper you shared with me on an axiomatization of path integral quantization and its equivalence to Berezin's quantization.
That's the one.
Now, I'll be honest, even the title sounds a little intimidating.
It's a mouthful, for sure.
Yeah.
But it's a fascinating paper. At its core, it's really trying to get a grip on this whole quantum behavior thing, mathematically speaking.
Right, trying to make sense of it all, and that's where quantization comes into play.
Exactly.
But before we get lost in the weeds, could you give us a quick, layman's terms rundown of what quantization actually means when we're talking physics?
Okay, so quantization, at its heart, it's like taking those classical physics laws, the ones that work great for, big stuff.
Right, everyday stuff.
Exactly. And then we have to figure out how to make them fit into this weird, almost counterintuitive world of quantum mechanics.
Like jamming a square peg into a round hole?
Kind of, yeah. It's a real challenge trying to bridge that gap between these two ways of seeing reality.
And why is it so important that we do that? I mean, what's the big deal with understanding the universe at that level, at the quantum level?
Well, for one thing, it's like unlocking the secrets to some of the biggest head-scratchers in science.
Okay, like what?
Think. How particles interact, how energy gets passed around, even the very essence of space and time.
Whoa, big stuff.
Big stuff.
Yeah.
And it's all tied to quantum mechanics.
So, if we can wrap our heads around quantization, we're essentially getting a glimpse of the universe's source code, in a way.
Precisely. And that's what makes this particular paper so intriguing.
How so?
It suggests a way to make this whole process of quantization, more rigorous, more systematic.
More user-friendly.
In a way, yes. It's like providing a clearer set of instructions, specifically for something called path integral quantization.
Now, from what I gathered, it seemed like this paper tries to make quantization more approachable. Would that be right?
You're spot on, yeah. It's all about providing a framework that's a bit easier to grasp, a bit easier to use for this complex mathematical tool.
Okay, I'm hooked already. Now, I noticed the paper's abstract mentions something called Berezin's quantization and these things called coherent states. Can you break those down for us?
Sure. So the paper's main goal is to axiomatize path integral quantization, right? And to do that, it creates a parallel with Berezin's quantization. But to get Berezin's quantization, we got to understand coherent states.
Okay, so walk me through these coherent states.
Imagine a giant orchestra. Hundreds of musicians, but they're not playing together. They're all just playing random notes whenever they feel like it.
Total chaos.
That's kind of what the quantum world is like, just this jumble of probabilities and uncertainty. But then imagine the conductor walks in and for a brief moment gets everyone playing the same note perfectly in sync.
A flash of perfect harmony.
Exactly. That's your coherent state. There's a little pocket of order in the quantum craziness.
So we're finding order in the chaos. I like it.
And the cool thing is, these coherent states, they're super useful for describing quantum stuff. They help us build a bridge between the weirdness of quantum mechanics and the more familiar world of classical physics.
A bridge between two worlds. That's a good way to put it.
That's the idea, yeah.
Okay, so how does this all loop back to path integral quantization? Where do the paths come in?
That's where things get really interesting, and that's exactly what we'll unpack next.
All right, you've definitely piqued my curiosity. Let's get into those paths. All right, so we've got these coherent states, these little islands of order in the quantum sea, but how does this paper actually use them when it comes to path integral quantization?
That's the crux of it. To really grasp that, we've got to get a feel for path integrals themselves.
Okay, back to basics then.
In a way, yeah. See, in classical physics, we're good with objects moving along a single path. Nice and predictable.
Right, like a basketball arcing through the air, easy peasy.
Exactly. We can track that bad boy from the player's hand right into the net.
Newton's laws, boom, we've got it down.
Nailed it. But in the quantum world, well, things get a bit more, shall we say, adventurous.
Adventurous, try mind-bending.
That too. Instead of one path, our quantum particle decides, nah, I'm going to explore every possible path at the same time.
Hold on, like every single path. That's a lot of detours.
Tell me about it. Imagine that basketball taking every route imaginable to the hoop, over the roof, through the stands, maybe even a quick loop around the parking lot.
Okay, my brain's starting to hurt. So how do we even begin to make sense of that, all those paths?
That's where our friend, path integral quantization, steps in, courtesy of the brilliant Richard Feynman.
Feynman, wasn't he the bongo-playing physicist?
The one and only. And besides his musical talents, he gave us this way to calculate the probability of a quantum particle going from point A to point B.
Okay, how?
By adding up the contributions from all those zany paths connecting the 2 points.
So we're basically saying, forget about following one path, let's just throw a giant quantum net and see what we catch.
You got it. And guess what makes this whole process a bit more manageable?
Don't tell me coherent states.
Ding, ding, ding.
Oh.
We've got a winner. Using those coherent states, we can actually simplify this whole summing over infinite paths business.
So they're like a filter for the quantum chaos.
That's a great way to put it. They give us a more workable set of states, make the whole path integral approach a bit more down to earth.
Down to earth in the world of quantum mechanics, that's saying something. Okay, but I got to ask about this classifying map thing. A paper mentions it with coherent states, and that one sounds even, I don't know.
Yeah, I mean, that's getting into the mathematical a bit, but it's an elegant idea, really.
Elegant, huh? You're going to have to sell me on this one.
Picture this. You have a map of, say, a city, nice and flat, right? Now, you want to project that onto a globe.
Okay, I'm following.
That classifying map, it's like the mathematical instructions for going from that flat map to the curved surface of the globe.
So we're basically talking about translating between different ways of representing the same thing.
You're catching on quickly. In this paper, that classifying map helps us see how points in one space, say the coherent state space, match up with points in another space, the quantum system we're studying.
A quantum address book.
I like that. And the paper uses a specific example, CPN, it's a kind of mathematical space, to show how this mapping actually works.
Okay, so we're starting to see how this paper is weaving together all these threads, coherent states, path integrals, classifying maps. It's like quantum mechanics meets arts and crafts.
Huh. I like the way you think. But you're right, this paper is all about finding the patterns, making those connections within this intricate quantum tapestry.
And the best part, it's not just theoretical, right? This paper actually takes these ideas and applies them to, actual examples.
Absolutely. That's where it gets really exciting. We're talking about the wonderful world of Poisson manifolds.
Poisson manifolds? Now, there's a term I haven't heard in a while, actually. Scratch that. Never. Break it down for me.
Okay, remember we talked about manifolds earlier, like that beach ball?
Yeah, good times.
A Poisson manifold, well, it's a special type of manifold with a little something extra, a structure that lets us define a certain kind of mathematical operation.
A little extra oomph, you could say.
Precisely. It gives us a framework for how things change or evolve on that manifold.
Okay, so we've gone from basketballs to beach balls to, I don't even know what a Poisson manifold looks like. This deep dive is living up to its name.
It's quite a ride, isn't it? But that's the thing about theoretical physics. It takes you to some wild places. And this is where it gets really cool.
Don't leave me hanging.
This paper takes our friend the two-sphere, our trusty beach ball, and uses it as a Poisson manifold to apply all these mind-blowing ideas to calculate something called the propagator for the system.
The propagator? Remind me what that is again.
Basically, it tells us the probability amplitude for a quantum particle to travel between 2 points on our sphere's surface.
So we're seeing how these big brain mathematical tools can be used for something as concrete as, what, a quantum particle rolling around on a beach ball.
You got it. And it gets even more interesting than that.
This is where it all starts to click for me. We're talking about these, like, really out there mathematical ideas, but then you're showing how they actually apply to a real physical system. Pretty amazing.
It is, and it gets even cooler. By applying this to the two-sphere, the paper starts to connect some other big ideas in physics.
Oh, like what?
Concepts you even mentioned earlier, the non-commutative product and those Pauli matrices.
Right. Those rang a very, very distant bell from my physics days.
Well, those are central to how we understand quantum mechanics, the non-commutative product, in the simplest terms.
Hit me with it.
It means the order you do things in, it matters. It's not like adding numbers.
Okay, so it's not like 2 + 2 = 4 no matter what.
Exactly. It's more like, imagine putting on your shoes and socks. You do it in the wrong order.
You're going to have a bad time.
Exactly. You get a totally different result.
Makes sense. Now, the Pauli matrices, those are something to do with spin, right?
You got it. They're these mathematical objects key for describing a particle's spin, which is, its own angular momentum.
Right, and that spin, it's quantized, right? Meaning it can only be certain values.
You're on fire today. Can't just be any old spin speed.
So what you're saying is this paper shows how those concepts, which are crucial for things like particle physics, they kind of pop out naturally from this whole quantization on Poisson manifolds thing.
Nailed it. And it doesn't even stop there. The paper dives into something called Berezin Toeplitz quantization.
Okay, try saying that 3 times fast.
Right. But it's a way to basically approximate, to get a handle on more complex quantum systems.
So it's like a shortcut instead of trying to map out every single detail.
Exactly. Think of it like trying to map all the stars in a galaxy. Berezin Toeplitz quantization is like having this super-powered telescope.
Okay, I like where you're going with this.
It lets you see further, clearer, even if you can't chart every single star.
That's got to be a pretty handy tool to have in your physics toolbox.
You can say that again. And the beauty is, it comes from these elegant mathematical ideas we've been unpacking.
Man, this has been quite a deep dive. We've gone from the subatomic world to, well, spheres, from orchestras to star maps.
It's been a journey for sure.
And all along the way, seeing how this paper shines a light on this whole idea of quantization, how we make sense of it.
It really highlights how powerful math can be, right? For understanding the universe.
Totally. It makes you wonder, if we can use this math to understand quantum stuff on a sphere, what other hidden connections are out there?
Right. What other shapes, other structures in the universe can we apply this to? It's pretty mind-blowing when you think about it.
Absolutely mind-blowing. Well, you've definitely given us a lot to chew on today. Thank you so much for guiding us through this.
Happy to do it. These are the kinds of conversations I love.
And for our listeners, we hope this deep dive has hopefully sparked your own curiosity, given you a new way to look at the quantum world.
It's a wild world out there.
It sure is. And until next time, keep exploring.
Hey everyone, and welcome back. We're diving into a paper today, asking, what if 2 completely different ways of looking at the quantum world, are actually the same?
Interesting.
Yeah, the title is, bear with me, on an axiomatization of path integral quantization and its equivalence to Berezin's quantization.
Okay.
Quite a mouthful.
Yeah.
But trust me, the ideas are even wilder.
Yeah, it's like finding out that 2 explorers, charting these separate paths through an uncharted jungle, end up mapping the same hidden temple. This paper is suggesting that paths and coherent states, 2, seemingly distinct paths in the quantum jungle, lead to the same destination.
Okay, now you've definitely got me interested. So for those of us who haven't exactly, spent our mornings with a physics textbook, could you break down those 2 approaches? What are paths and coherent states, like in quantum mechanics?
Yeah, you got it. So imagine trying to understand the movement of, like, a tiny particle, like an electron, in the quantum world. Now, in our everyday world, if you want to go from A to B, you take, like, the most straightforward path, right?
Right. Okay. Makes sense. Why waste the time and energy?
Exactly. But in the quantum realm, things get a little weird. Path integral quantization says that instead of just taking one path, the particle considers all possible paths.
Wow.
Even ones that seem crazy, like taking a detour through a wormhole,
What?
a shortcut through space-time. And each of these paths contributes a tiny bit to the probability of the particle actually ending up at point B.
So it's like this particle is a tourist who wants to explore every single possibility, every nook and cranny of the universe on its way to just like the grocery store.
Yeah, that's a really fun way to think about it.
Yeah.
Now, Berezin's quantization, on the other hand, that's like finding those rare pockets of stability in the quantum storm. It focuses on these things called coherent states, which are the closest you can get to having a well-defined, predictable state in the quantum world.
So if path integrals are about embracing the wild possibilities, coherent states are about finding the eye of the storm.
Yeah, precisely. They're like the points where that fuzziness of the quantum world starts to resemble the more, predictable world that we experience.
And this paper argues that these two wildly different approaches are actually equivalent.
Hmm.
That's a very big claim.
It is. And to understand why it's so significant, let's dive into the mathematical framework they use to connect these ideas. Symplectic manifolds and pre-quantum line bundles.
Okay.
Don't worry, I promise to make it as painless as possible.
All right, I'm ready to enter the mathematical jungle. Lead the way. Okay, so you mentioned symplectic manifolds. What exactly are those? What role do they play?
Symplectic manifolds are kind of like the stage on which like the drama of classical physics unfolds. Imagine like describing the motion of a ball rolling down a hill. You'd need to talk about its position and its velocity at any given moment, right?
Yeah, I mean, those seem like the basics.
Exactly. So a symplectic manifold provides that mathematical framework to describe that motion. It's like it captures all the possible positions and velocities the ball could have as it rolls down that hill. It's like the set of all possible states of our system.
Okay, so we've got the stage, like our symplectic manifold. So how do we bring those quantum tourists we were talking about onto the stage?
Right.
That's where the pre-quantum line bundles come in.
Yeah.
You got it. To, well, to work with these classical spaces in the quantum realm, we need to, like, incorporate quantum information somehow. This is where the concept of pre-quantum line bundles is really crucial. Think of it like this. Imagine that at each point on our stage, we attach a tiny arrow. The direction of this arrow gives us an extra layer of information, a way to encode those quantum possibilities that we talked about.
Right. Yeah.
That's essentially what a pre-quantum line bundle does. It's like it adds a sprinkle of quantumness to our classical stage.
So it's like we're taking this classical play and adding in some special effects, some quantum twists and turns to the storyline.
Right.
And this paper uses these tools, symplectic manifolds and pre-quantum line bundles, to show how those two different quantization methods are connected. Precisely.
Yeah.
Yeah, what's really remarkable is that the researchers found a way to describe this, quantization process, taking something classical and making it quantum, using both path integrals and Berezin's coherent states.
Wow.
It's like discovering that two different sets of stage directions lead to the same quantum performance.
This is really blowing my mind a little bit. So even though these shapes seem so different, the math is kind of telling us that they share something fundamental in this quantum world.
Absolutely.
So tell me a bit more about these specific shapes. Like, I know you mentioned that the researchers applied this to the two-sphere.
Yeah, and the two-sphere example is particularly fascinating.
Good.
Picture, the surface of like a perfectly round ball.
Okay, sure.
Now, you might be thinking, like, what's so special about that? But here's where it gets interesting.
All right, I'm intrigued.
Well, when they quantize this two-sphere using, both of these methods, and they compare the results, this remarkable connection emerges. The math starts to echo something called the Pauli matrices. These are these fundamental objects in quantum mechanics that describe the spin of particles, like electrons.
Hold on. Are you saying that by quantizing something as simple as a sphere, we stumble upon something as fundamental as the spin of an electron?
Yeah, it's really wild.
That's crazy.
You see, the Pauli matrices are like these tiny quantum switches that govern how particles behave in magnetic fields.
Okay.
They can be in one of two states, spin up or spin down, and these states determine how they interact with their surroundings.
So it's like the shape of that sphere is somehow encoded in the very essence of these quantum switches.
In a way, yes. And the paper doesn't stop there. They go on to show that this connection between path integrals and Berezin's quantization holds true for a whole class of shapes called surfaces of constant curvature.
Surfaces of constant curvature. Okay, I need to brush up on my geometry here. What exactly does constant curvature mean?
Yeah, you're in luck because I find this stuff fascinating. So constant curvature essentially means that the surface has like the same amount of bend at every point. Think of a flat plane that has zero curvature.
Okay.
Now imagine bending that plane into a sphere.
Right.
That's an example of constant positive curvature.
So a sphere, like our two sphere, that has a constant curvature, what about other shapes?
Right. So there are also shapes with constant negative curvature, like saddles or, those funky Pringles chips.
Yeah.
A little trickier to visualize, but they exist, in this mathematical space.
So we've gone from quantizing, like beach balls, to quantizing saddles. Why is it significant that this equivalence holds true for this whole class of shapes? What does it actually tell us?
Well, it suggests that this connection between path integrals and Berezin's quantization isn't just a coincidence. It's not just a fluke that happens to work for a few special cases. It hints at a much deeper, more fundamental relationship between these two approaches. It's like discovering that two different languages share the same underlying grammatical structure.
Oh, that's a great analogy.
Right.
So we've established this pretty amazing link, but I imagine there's still so much more to uncover. What are some of the unanswered questions that stem from this research?
Yeah, that's the beauty of scientific discovery, isn't it?
It really is.
Yeah.
So you're saying that even with this, breakthrough, there's still, plenty of uncharted territory in our quantum jungle.
Oh, absolutely. I mean, for one thing, while this paper demonstrates this equivalence for a pretty fascinating range of examples, it doesn't necessarily mean that it holds true in literally every single case.
So there might be some quantum shapes out there that, defy this connection. What are some of the limitations that we're, bumping up against here?
That's a key question for future research, right? I mean, are there certain types of shapes or certain quantum systems where these two approaches might diverge, giving us different answers or insights? It's like we've drawn this really detailed map of this quantum terrain, but there might be some hidden valleys or treacherous peaks that we haven't even begun to explore.
And each new discovery could, totally shake up our understanding of the quantum world. What about, the bigger picture? You mentioned this research could have, implications for fields like string theory and quantum gravity. How so?
Well, imagine trying to describe something as fundamental as space-time itself.
Yeah.
The fabric of the universe.
Right.
In a way that's consistent with, all the bizarre rules of quantum mechanics.
Right.
That's the challenge these fields are grappling with.
Yeah, no small feat.
Right.
And you're saying this newfound equivalence between path integrals and Berezin's quantization might actually give physicists new tools to kind of tackle that challenge.
Exactly. I mean, each of these approaches has, its strengths, its weaknesses, but now we know that they're fundamentally connected, which could spark entirely new lines of inquiry. It's like having two different sets of lenses, each revealing these different aspects of the same intricate structure.
So by combining those perspectives, we might finally be able to see, the quantum nature of space-time in sharper focus. That's incredibly exciting.
It really is, and it highlights the power of theoretical physics,
Yeah.
These seemingly abstract mathematical explorations have the potential to revolutionize our understanding of the universe at the most fundamental level.
This whole deep dive has been a mind-bending journey. We've journeyed from this strange world of quantum paths to the elegant mathematics of symplectic manifolds. And we even glimpsed the potential these ideas have to, unlock some of the biggest mysteries in physics.
And the best part is this is really just the beginning. I mean, this research opens up this whole new avenue for exploration. Who knows what incredible discoveries await us down the road.
That's the beauty of science. There's always more to learn, more to discover. So for our listeners who, are ready to continue this adventure, we'll be sure to link to, the research paper and some other resources in the show notes.
And as always, keep asking those big questions and never stop exploring.
Until next time, happy deep diving. Hey everyone, ready to dive into something kind of wild? We're talking path integral quantization today.
Path integrals, huh? Yeah, those will stretch your brain a bit. It's like particles decided, why choose one path when I can take them all?
Right. It's like they're trying out every possible route all at the same time. Sounds messy, but there's a weird order to it.
Quantum chaos, but with hidden patterns. That's the fun part.
Exactly. And that's where our deep dive comes in. We're looking at this paper by Joshua Lackman, trying to wrangle some of that elegance out of the chaos.
Let me guess. on an axiomatization of path integral quantization and its equivalence to Berezin's quantization. Catchy title, right?
You
Right.
got it. But don't let the jargon scare you. We're breaking it down. So, before we go too deep, quick reminder. Path integral quantization. What's the gist?
It's like instead of just saying the particle went from A to B, you got to consider all the zigs and zags, the loops, the detours, everything it could have done factors in.
Like a quantum choose-your-own-adventure, but you read every path at once.
And somehow, from that mess, you get actual probabilities of things happening.
Mm,
Wild, right?
right, totally. This paper focuses on a type called coherent state path integrals. What's so special about these coherent states?
Think of a laser pointer, that nice focused beam. That's a coherent state of light, much more organized than, say, the light from a light bulb.
Okay, so bit of order in the quantum soup.
Yeah, these coherent states for particles are like that laser, a more stable, well-defined way to describe them. But even then, calculating these path integrals, oof.
It's a headache, isn't it? The
Mm.
math gets messy fast.
That's putting it mildly. That's where Lackman comes in with these axioms, like a set of rules, a checklist for what a valid path integral has to satisfy.
So he's like, hold on, quantum chaos aside, these rules always apply.
Exactly. It's not just about crunching numbers and hoping for the best anymore. These axioms are like, does your answer make sense given the rules of the game?
Okay, I like that. A quantum rule book. What kind of rules are we talking about?
One of the big ones is the idea of being Hermitian. It's getting a bit into the weeds, but it basically makes sure our calculations give us real, measurable results.
So grounding things in reality, even when we're in the quantum realm.
Yeah.
Makes sense. What else?
Continuity. Like imagine drawing a line on a graph. You want it smooth, no sudden jumps, valid path integral. Same idea, mathematically speaking.
Gonna keep things flowing smoothly, even through all those possible paths.
Right. Another important rule, or axiom, in Lackman's framework is being localized. Basically, the calculation should have peaks that tell you these paths are the most likely ones.
So it's not just that every path is equally important, but that some matter more than others.
Exactly. Localization helps us understand why, even with infinite possibilities, we see some outcomes more often.
This is fascinating. It's like Lackman took this crazy idea and gave us a map and compass to navigate it.
Exactly. And it gets even wilder. He connects it to another big idea, Berezin's quantization. Ever heard of it?
Oh, I've seen the name, but it always seemed kind of intimidating, to be honest.
It can be. Instead of summing over all those paths, Berezin's approach uses operators, think of them like mathematical actions, in a special space called a Hilbert space.
Okay, so two totally different ways of looking at the quantum world.
Right. And here's where Lackman's work is truly mind-blowing. He found that they're basically the same thing. Like finding a path integral that follows all those rules, those axioms we talked about, it's equivalent to doing Berezin's quantization. Two sides of the same coin, who knew?
Wait, hold on. Back up a bit. You're saying those two approaches, the paths and the operators, they lead to the same result.
That's what Lackman's showing. It's like finding this hidden tunnel connecting two places you thought were miles apart. A major link nobody saw before.
Okay, that's kind of mind-blowing. We're really starting to see the connections here, how it all fits together.
Right. And it gets even cooler. See, one of the tricky things is quantizing curved spaces. Like, how do you do path integrals on a sphere?
Quantizing a sphere. Okay, now we're getting weird. Why even worry about that?
It's more common than you think. Lots of quantum systems, they have this spherical symmetry. Electrons around an atom, for example, spheres are everywhere.
Okay, I get it. But doing those path integrals on a curved surface sounds like a headache.
It's a mess. The usual tricks just fall apart. You need a whole new set of tools.
So how do you even approach that?
Lackman uses something called the Bergman kernel. Ever come across that one?
Vaguely. Rings a bell. Refresh my memory.
Basically, it's this mathematical gadget that lets you define a path integral on a sphere without everything going haywire. It's like, you know how maps of the Earth get distorted?
Yeah, trying to flatten a globe never works out right.
The Bergman kernel helps you translate between the flat math we're used to and the curved reality of that sphere.
Clever. So it's not just a one-off trick, right?
Exactly.
This connects to other stuff, too.
You got it. This whole Bergman kernel idea, it ties into something called Toeplitz quantization, another way people have tackled curved spaces in quantum mechanics.
So it's like he's building bridges between different parts of the field, showing how they're all related.
Exactly. And it doesn't stop at spheres. This framework, it works for other weird spaces too. The complex, plane, even hyperbolic space, the kind of geometry Einstein used for gravity.
Hold on. Are we saying this path integral stuff could be connected to quantum gravity?
But now you're getting it. It's a serious possibility. This paper's showing us how deeply linked path integrals are to the shape of space itself.
So the fabric of the universe, all those curves and warps, maybe comes from quantization. That's huge.
It's a wild thought. This paper doesn't give us all the answers, but it's opening up new ways to think about the universe at its most basic level.
This is incredible. We were talking about other examples. What about this poodle sphere thing? Sounds like something out of Star Trek.
Right. Sounds like a weaponized planet. But seriously, it's this super abstract mathematical idea. Imagine a sphere, and then you curve the surface of that again. It's like curved space on top of curved space.
Okay, my brain's hurting a bit. Why is this poodle sphere important?
Because Lackman's framework still works there. Even in this crazy abstract space, his path integral approach makes sense. It's like having a universal translator for quantum mechanics.
So we're seeing it in action, not just for familiar stuff like spheres, but for these really out there mathematical spaces too. And maybe even for space-time itself.
Exactly. That's why this is so important. It's not just about finding the right equations. It's about understanding how those equations reflect the nature of reality.
It's like uncovering a hidden language, something that speaks to how math and quantum mechanics and maybe even reality itself are all connected.
Beautifully put.
This whole idea that quantization could be behind the shape of the universe itself, it's mind-blowing. Like, the universe isn't just playing by quantum rules, it's that the playing field itself is made of those rules.
It's a huge idea, no doubt. And Lackman's work, giving us this framework, these connections between different approaches, it's a whole new way to think about these fundamental questions.
Liz, maybe we don't have all the answers yet, but this research is pushing us closer to understanding how it all works deep down.
Definitely. It reminds you, even when you're deep in the weeds of theoretical physics, these elegant connections are out there, just waiting to be found.
And who knows, maybe someday, research like this will help us crack the code of quantum gravity, figure out how it all fits together.
That's what's so great about science, right? The journey never really ends. Always more to discover, more connections to make.
That's why we love these deep dives.
Yeah.
Huge thanks to you for walking us through this stuff. Path integrals, axioms, quantizing the universe. It's a lot to wrap your head around.
Happy to do it. Always a pleasure to geek out about this stuff.
And to everyone listening, keep those big questions coming. Keep exploring. You never know what amazing connections you might find out there.
Absolutely.
Until next time, keep diving deep.